Hello, everyone. This is Qizhen from HKUST and Alibaba Group. It's a pleasure to share our observation on the machine learning as a service platform and discuss workload scheduling in large and heterogeneous GPU clusters with you. My co-authors are Wencong, Yinghao, Wei, Chen, Jian, Yong, Liping, Wei, and Yu. In large e-commerce and IT companies like Alibaba, machine learning empowers a multitude of applications like image recognition, language processing, and recommendation. The usage of massive datasets, increasing from gigabytes to hundreds of terabytes, not only helps algorithms make great breakthroughs, but also forces the jobs to scale out to a large number of GPU machines, which impose great challenges to the cluster, such as GPU GAN scheduling. Alibaba Pi stand up to these challenges and provide an all-in-one platform over a large-scale GPU cluster. The figure on the right shows the overview of Pi. At the top user level, Pi can host both training and inference workloads and support a variety of machine learning frameworks such as TensorFlow, PyTorch, GraphLearn, etc. The submitted jobs are split into tasks with different roles like parameter server, worker, evaluator. Then the instance of these tasks are put into containers and scheduled onto heterogeneous nodes. The traces has been released on GPU on GitHub. Let's take a look at the trace basics first. Collected in July and August 2020, the traces covers 1,800 nodes and over 6,700 GPUs. The table on the right shows the detailed specification of these machines. They are equipped with different number of CPUs and main memory, and covering a variety of GPU types like NVIDIA V100, P100, T4, and miscellaneous GPUs of older generations. On the user side, over 1,300 users have submitted 1.2 million tasks with over 7.5 million instances. Users can specify task GPU type and whether to share GPUs with other workloads. The table below is a sample job specification with two types of tasks. Note that the majority of tasks require multiple instances to be launched at the same time, which is called GAN scheduled. The figure on the right shows the CDF of the number of GAN scheduled instances. We can see only 15 instances are single ones, 85% are GAN scheduled. Regarding the pattern in runtime and queuing delay, we observe that instance runtime ranges from seconds to hours, which is similar to former observation in Microsoft Philly, as shown in Figure A. While compared with their queuing delay in Figure B, we find tasks with below medium runtime spend a larger proportion of their runtime in waiting. The queuing delay is also correlated with specification of GPU amount and type, as shown in Figure C and D. Tasks requiring full GPUs or high-end GPUs wait longer. Regarding the resource requirement, we plot the distribution of total CPUs, GPUs, and memory requested by all instances by blue solid line. In A, B, C figures on the right, it can be observed that all these three distributions are heavy-tailed, with around 20% instance requesting large amount of resources. As for the real usage plotted in the orange dotted lines, it shows that most users tend to ask for more resources than they actually needed, resulting in a low resource utilization. Therefore, in Pi, we allow instances to use spare resources in the host machines and make it possible to overuse what they requested. In the Figure D, we measure the difference between instance resource usage and request for CPU, GPU, and memory. Positive means overuse, and normalize it with machine's resource capacity. We found 19% instance overuse CPUs, while only 3% use more GPUs than requested. Let's then look from the machine's perspective. At each time step, we collect the utilization of all 8 GPU machines and calculate the tail at the P90 and the median at the P50 utilization. The plot the result on the left figures. It shows 8 GPU machines are high in both CPU and GPU utilization. Similarly, we do the analysis for 2 GPU machines and plot the result on the right figures. It shows two GPU machines are high in GPU but medium in CPU utilization. Also, we observe a larger variation in GPU utilization by measuring the gap between P90 and P50. It is partially due to the bursty GPU usage patterns found in our workloads, and also due to the design of our scheduler. By the way, the main memory and GPU memory seem well provisioned in our cluster, as well as network bandwidth and disk I/O. In the remaining time, we are going to present two opportunities we found towards better efficiency and discuss several challenges we met. Pi supports GPU sharing, which allows multiple instances to run on the same GPU with time and space multiplexing. In specific, co-located instances are guaranteed to have a share of the GPU memory, which is space multiplexed. While in the runtime, the compute units like streaming multiprocessors are dynamically shared among those instances, which is time multiplexed. To show the benefits of GPU share, we plot the allocated GPU number in each hour based on the real measured values in yellow boxes. We add the simulated result in green boxes, showing the number of GPUs requested for the whole cluster if there were no GPU sharing. It shows on average 2 times of GPUs would be needed if there were no sharing. In peak hours, GPU sharing could save over 2,500 GPUs. Some may ask, does GPU sharing cause contention? We would say yes, but this is mild. We plot the distribution of all GPUs in the left figure, which shows heavy utilized ones, over 95% utilization ones, only account for 7% cases. Among those 7% cases, we further divide them into two groups shown on the right. GPUs with 2 or more instances co-located are on the top of the bar. Within a 5-day period, only around 4% of heavily utilized GPUs host multiple instances. We therefore believe GPU sharing does not cause severe contention in our cluster. Another opportunity we find is that most tasks are recurring. Recurring tasks have similar meta-information across multiple submissions, such as entry, script, command line parameters, data source, and sinks. Based on this, we made a group tag for each of them and summarized their occurrence in the left figure. It shows over 65% tasks have repeat for over 5 times. To be more intuitive, the figure on the right shows the submission pattern of 3 recurring tasks doing batch inference. We can see they run on a regular basis, like once a day or once for 2 hours. They also have quite stable runtime. We therefore predict the duration of recurring tasks from past runs. We use a regression tree as the predictor and feed it with features like the group tag, the task username, and the resource request. The figure on the right top shows the more feature it uses, the better estimate it could make. In the best cases, the error for 78% instance falls within 25%. Guided by this duration prediction, we simulate the scheduling with shortest job first policy. It shows on the right bottom figure, compared to the FIFO baseline, SGF scheduler can reduce the average task completion time by 63 to 77% with the same number of GPUs, or achieve similar performance with less than 1/3 GPUs. However, our design is not without problems. We next design some open challenges which we believe also stand in other GPU clusters with heterogeneous machines. First and foremost, we find CPUs can be the bottleneck in such GPU cluster. We first observe it from the popular CTR prediction tasks, whose runtime is plotted on the right. The blue solid line shows the machine-level CPU and GPU utilization of delayed tasks, whose duration are the longest 15% in the recurring job. We observe a strong correlation between CPU contention and instance slowdown, while GPU contention, on the other hand, has no clear contribution to it. Then we examine a variety of recurring tasks on different nodes, which are shown on the bottom. We find a similar phenomenon. In general, machines running delayed instances measure higher CPU utilization than those running accelerated or normal instances. However, such correlation is not found on GPUs, Therefore, CPU is more likely to be the performance bottleneck. What are the causes behind? From the perspective of workload, there are a majority of tasks running in a cluster are of high CPU but low GPU. We benchmark several typical tasks and show their runtime breakdown as follows. CTR tasks could spend around 80% time on CPU doing prefetching and pre-processing, since their inputs are usually large but sparse. For graph neural networks, the CPU operation also accounts for 30 to 90% time, varying from different models. The algorithm will iterate over edges and simple neighbors before their GPU operations begin. There are also many reinforcement learning tasks here. C usually generates a large amount of data through parallel simulation on the CPUs and performs training on GPUs. This eats up lots of CPU and memory bandwidth, but only a small fraction of GPUs. From the node and scheduling perspective, we summarize the machine specification and the instance resource request on the right table. Although the cluster-wide CPU to GPU specs, which is 23.2, remains close to the overall instance request, which is 21.4. Still, there is a mismatch between nodes and their workloads. In 8 GPU machines with 96 CPUs, the CPU-GPU ratio is 12. However, the instance running on those machines requests 22.8 vCPUs per GPU on average, which makes the nodes overcrowded. We can see this more clearly on the heat map below. Each row corresponds to one machine. The rows are divided into 4 groups, namely CPU request, CPU usage, GPU request, and GPU usage, from top to bottom. The x-axis shows each hour in 20 days. The darker the color, the higher the utilization or allocation rate is. In Figure A, on the nodes with 8 older generation GPUs, over 75 CPUs and GPUs have been allocated. However, comparing it with Figure B, we find high-end machines with advanced V100 GPUs are less crowded. Even within V100 machine groups, some nodes are idle and others are quite busy at the same time, showing the imbalance. This is because the scheduler tends to pack more workloads on low-end machines and use fewer high-end GPUs machines. In contrast, 2 GPU nodes in the Figure C and D are quite underutilized in CPUs. It implies the imbalanced scheduling. To take a closer look at the scheduling, there are 2 policies in the cluster. One is reserving and packing. It intentionally reserves high-end GPUs for high GPU tasks, like distributed large model training, and it packs other workloads to less advanced GPUs. Another is load balancing, which assigns instance to node with low allocation rate. Our scheduler prioritizes reserving and packing over load balancing. The reason behind is to avoid extremely long latency for multi-GPU tasks. Simulation shows for instance requesting V100 only, reserving and packing can reduce their queuing delay by 68% compared to load balancing. It can cut off the tail latency that are over 10,000 seconds. To summarize, we make a number of observations in our machine learning as a service platform. Firstly, a majority of tasks have non-scheduled instance, and most of them request small amount of GPUs. Secondly, we show that GPU sharing and duration prediction of recurring tasks can help improve the efficiency of the cluster. But still, we are aware of that CPUs could be the bottleneck, especially under imbalanced scheduling policies. We are happy to announce that the traces has been released on GitHub, and looking forward to the discussion and possible collaboration in the future. Thank you.